Welcome to iLecture Online, and here's combination number 3 for lens combinations. In this case, we are going to combine a converging lens with a focal length of 20 centimeters and a diverging lens with a focal length of minus 30 centimeters. Remember, converging lenses are positive lenses, diverging lenses are negative lenses. Now, when you put a converging and diverging lens together, they kind of counteract with each other because a converging lens causes the rays to converge and the diverging lens causes the rays to diverge. And as a combination, will they act like a converging lens or a diverging lens? And that depends upon their relative strengths. The smaller the focal length, the stronger the lens is, the more it will cause the rays to bend. So in this particular case, it looks like the converging lens is stronger than the diverging lens, and so the end result is, as a combination, the two lenses will still act like a converging lens, but the second lens, diverging lens, will kind of dilute in a way the strength of the first lens, which means that the rays will not converge as quickly, and the image will probably be formed farther away. So let's see if we're correct on that one. If we only consider the first lens, let's find then the first image, and we do that by drawing a ray parallel to the normal till we hit the lens, and then the ray will diverge and go through the focal point on the other side, and so that would be ray number 1. Then we draw a second ray, which is from the object to the focal point on the front side of the lens, and so until we hit the lens, then the ray will diverge and continue on straight parallel to the normal. That would be ray number 2. There's the observer looking at those rays and says, sure enough, they come together, and so it looks like there's going to be an image formed right here, and that will then be considered image 1, and the distance from the first lens to the image will then be considered the image distance. Using our equation to quickly find out where that is, we can say that S1 prime is equal to S1 F1. Remember, S is the object distance, F1 is the focal length of the first lens, S1 prime is the distance to the first image, divided by S1 plus F1. Ooh, not plus, it's actually minus. Just like the equation says over there, it's minus. Plug it in the numbers. S1, we got 40 centimeters. F1 was a 20 centimeter lens, divided by 40 minus 20, so this is 800. Divided by 20, which is 40 centimeters. It's a positive 40 centimeters. Positive means it's a real image. 40 centimeters means it's 40 centimeters past the second lens. And so we can then say that this distance right here, which is the S1 prime, is equal to a positive 40 centimeters. Okay, now to find the image of the second lens. So in a way, what you can think about is, since these rays are converging right here, now they pass through a diverging lens, the rays will then be diverged to some extent, but not completely to the point where they'll be parallel to the normal. They'll continue to converge, but much more slowly, and the image will be formed farther away. So let's see if that is indeed true. Before we do that, though, I'd like to calculate maybe the magnification of the first lens. And so, first of all, this is a real image. And the magnification M1 is equal to minus S1 prime over S1, which is a minus 40 divided by 40, which is a minus 1. And so what that says is that the image is inverted, but the size is exactly the same as the object that caused it. So the size of the image is the same as the size of the object, at least for object 1 and image 1. All right, now doing the same thing with the second equation, we can say that S2 prime is equal to S2 F2 divided by S2 minus F2. And so S2 is, we don't know yet. Where is S2? Well, it turns out that image 1 now becomes object 2. And so the distance from the object to the lens would now be this distance right here. And that distance is called S2. And notice that this is 40 centimeters. The distance between the lenses is 10 centimeters, so S2 is 30 centimeters. However, since the object is behind the lens, that becomes a negative object distance, so negative 30 centimeters is the correct object distance for lens 2. So S2 now becomes a minus 30. We subtract from that, not subtract, we're multiplying in the numerator. So we multiply minus 30, because that is the focal length of the second lens, divided by a minus 30 minus a minus 30. Now here's an interesting situation. Let's see here. This is a positive 900 divided by a minus 30 plus 30, which is 0. Wow. What does that mean? We have a 0 denominator. That means the object or the image of the second lens is at infinity. That means that let's see here. Oh, that makes a lot of sense, because it turns out that the first image, which now became the second object, is exactly located at the focal point of the second lens, and it's a diverging lens, which means that, yes, indeed, the rays will be diverged in such a way that they will never come together, just continue on forever, and never form an image anywhere. So that means that the second image is at infinity, and we're not going to find it that way. All right, I guess I'll have to show you another example where that's not the case, and that way we can see how the second image forms. All right, so come back for the next video, and you'll see how we do another lens combination where we don't have an image at infinity.